We're back with video 4 from class 17. Here's an example from board acne, example 5.2. The refrigerator in a kitchen, shown in this figure, receives electrical input power of 150 watts. Is that a lot? I mean, there are light bulbs that are 150 watts to drive the system, and it rejects 400 watts to the kitchen. Find the rate of energy taken out of the cold space and the coefficient of performance of the refrigerator. So here you go. Here's your diagram of your source and sink. I guess we get the sources up here, and the sink is down there. I don't know. I don't think we would label them this way. But anyway, here's the little thing in the middle, the little refrigeration system that's making all this happen, making us go from a low to a high. Boom. So, I don't know. I went ahead and drew the thing. Why did I draw it? I don't know. Just want to, what goes on inside here? We already know, right? That we are taking this fluid out of here, called a refrigerant, and we're compressing it, and then it's taking heat out from someplace, and then we're expanding it, and then we're putting it right here. So I think I did that right. Now that I'm looking at this, I'm not going, dude, did you just draw this the wrong way? Let me see right here. 1 second. Well, that was ridiculous. Okay, I'm sorry. I was drawing it the wrong way. Yeah, there you go. I just described it the wrong way. That's all. Is anybody listening to me? I don't know. Anybody's listening to me. Anyway, we're putting work in to this thing. I guess it makes sense because we're doing the QL, and then we're doing the Q out, Q high. And we're writing that the work in is going to be equal to the heat out minus the heat in. So that difference in there, right? We're using that work in to propel the thing forward. So we could rewrite this around, and let's make them dotted because they're rates, right? We're at watts, so it's the rate of the thing happening. So we're going to say the low is going to be equal to the high. Is that right? Yeah, minus the in. Just double checking that. Does that work out with this right here? Yes, you just flip flop and get the signs. Okay, so we're going to say 400 minus 150. It's going to be 250. So that's the amount of heat that we're taking out of the bologna. All right, so here's your bologna right here. And here's your bottom of your refrigerator right here, or in the back, right? But a lot of times it'll be the bottom right there. It's like old school refrigerator. We'll be able to measure how well this thing does. We do the coefficient of performance, and this is for a refrigerator, also called beta in the Borgnacki book. And we take what we want, which is the QL, divided by what we paid for, which is the amount of power in. So we're moving 250 watts, and it took us 150 watts to do it. So we get a 1.667 is our coefficient of performance. Now, notice this is greater than 1. Oh, why is that? Well, I think it's because it's easier to move heat than it is to create work. Maybe that's one way. Someone asked in class why that was so. How can this be greater than 1? And I'm going to just mention, well, it's relatively easy to move heat, but it's quite challenging to create power. So that would be one just gut feel, easier, maybe way to describe it. Not necessarily mathematically rigorous treatment of the thing, but I think it is true. It's easier. It's a silly way to pronounce it. I don't know. That was my explanation. I'm going to ask Dr. Yavistrick what he thinks.